Welcome to our Quantum Deep Dive.
Hello.
Today we're diving deep into a really rapidly evolving space. It's where two super powerful fields are colliding. Hybrid quantum classical machine learning.
Right, sometimes called HQML.
Exactly, HQML. And for this deep dive, we're leaning on a really insightful essay by Jorgo Schneeppel.
Yeah, it does a great job sort of laying out the whole landscape of this fascinating frontier.
So our mission today really is to unpack the core ideas from that essay. We want to try and figure out, what is HQML really about? Why is it such a hot topic right now?
And what the future might hold as these technologies mature.
Yeah. I mean, machine learning, classical level has already changed so much, right? Recommendation engines, medical stuff.
Absolutely. And then you've got quantum computing, which, okay, it's still early days, but it promises a completely different way of doing computation.
Uh-huh.
So HQML is all about finding the smart ways, the clever ways, to use the strengths of both of them together.
Exactly. And this isn't just, abstract academic stuff. For you, the listener, understanding HQML could mean getting a handle on tech that might dramatically speed up data analysis.
Or solve problems we literally can't solve classically right now.
Right. And it could reshape industries. You deal with finance, healthcare, advanced manufacturing, you name it.
Okay, so maybe we should start by looking at the two worlds that HQML is trying to bridge.
Good idea.
Okay.
Let's start with the classical side, classical machine learning.
Yeah.
In a nutshell, what are we talking about?
Well, classical ML, it's basically algorithms that learn from data directly. They spot patterns, make predictions, make decisions, all without needing explicit, step-by-step instructions for every single case.
Okay.
You've got the main types, supervised learning, where you use labeled examples to predict things, unsupervised, which finds hidden patterns in data without labels, and reinforcement learning, where an agent learns by trial and error in some environment.
Got it.
Yeah.
But even with all those successes, classical ML does hit some walls, doesn't it? Especially when the data gets just enormous. What are the big challenges there?
Yeah, Schneeppel's essay points out a few key ones. There's the sheer computational power needed and scalability. Processing these massive data sets is just incredibly demanding, sometimes too demanding.
Right.
Then there's the whole black box issue. These complex deep learning models. It can be really hard to figure out why they made a certain decision. Interpretability is a big one.
Yeah, that seems crucial.
Definitely. And you often need huge amounts of really good labeled data, which isn't always easy to get, and of course overfitting.
Where it learns the training data too well.
Exactly. It gets too specialized and then fails when it sees new, slightly different stuff.
Okay, so challenges with scale, interpretability, data needs on the classical side. Now let's flip it, the quantum side. What are the kind of core ideas that make quantum computing so fundamentally different?
The absolute foundation is the qubit. It's not just a 0 or 1 like our classical bits. A qubit can be in a superposition of both 0 and 1 at the same time. You often see it written like psi wrangle, alpha wrangle, plus beta 1 wrangle.
That formula again, yeah?
Yeah, and those alpha and beta, they're complex numbers telling you the probability, sort of the chance. You'll get a 0 or 1 when you actually measure it.
Which is already pretty weird to wrap your head around.
It really is. And then there's entanglement.
Okay.
When qubits are entangled, they're linked. Measuring one instantly influences the other no matter how far apart they are. It sounds like science fiction, but it's real.
And that linkage is key.
It's a huge source of quantum power. It lets a small number of qubits represent a massive, exponentially large number of states simultaneously. And finally, there's measurement itself. When you look at a qubit, it snaps out of superposition.
It collapses.
Exactly. It collapses into a definite 0 or 1 based on those probabilities, alpha and beta.
And what kind of actual machines are doing this stuff today? What's the hardware look like?
Well, the leading contenders right now seem to be systems using superconducting qubits. You hear about IBM and Google working on those. And also trapped ions, which companies like IonQ are known for. And we know there are these powerful theoretical algorithms like Shor's for factoring.
Which could break encryption, potentially.
Right, that's the famous one. Or Grover's algorithm for searching databases faster. They hint at the kind of speed-ups quantum could theoretically offer for certain problems.
Okay, so classical ML dealing with big data, optimization issues, and quantum computing with these strange qubits, superposition, entanglement. These seem like totally different universes. How do they even connect?
That's where it gets really interesting and kind of surprising. The essay points out there's actually a lot of overlap in the mathematics.
Really? How so?
Both fields rely very heavily on linear algebra.
Matrices and vectors.
Exactly. Vectors, matrices, transformations. Quantum states are vectors in this abstract space called Hilbert space. And ML models, especially neural nets, are basically doing tons of matrix multiplications and vector stuff.
So they speak the same mathematical language in a way.
Pretty much. And both are super concerned with optimization problems.
Okay.
In ML, you're always trying to minimize some cost function, right? Like J theta, to train the model, find the best settings.
Yeah, tuning the model.
And in quantum computing, lots of problems, like finding the lowest energy state of a molecule, the ground state, can also be framed as optimization problems.
Okay. So the connection isn't just conceptual. It's down in the mathematical weeds. And that common ground lets them, work together.
Exactly. That's the synergy. You use the quantum computer's potential power to speed up specific bits of an ML task.
Not the whole thing.
Not the whole thing, no. Or you use classical computers to manage the complexity and, frankly, the current limitations of quantum hardware within some kind of hybrid loop.
Right.
Like maybe a quantum algorithm could solve systems of linear equations way faster, which is something that pops up in classical methods like support vector machines, SVMs.
Right. I remember that being a bottleneck sometimes.
Or a quantum computer might efficiently calculate some specific value that a classical optimization routine needs to keep going.
This leads us right into the main topic then. Hybrid quantum classical machine learning, HQML.
Exactly.
So what's the official definition?
Well, at its heart, HQML is about integrating classical ML techniques with quantum computing principles. The whole point is to tackle problems that are either just impossible, intractable, or super inefficient for classical computers alone.
But it's key that it combines them, right? It doesn't just throw out the classical part.
Absolutely not. It uses the strengths of both. With today's tech, you really can't run a whole complex ML model just on a quantum chip.
So how does it actually work? What's the flow?
The typical setup, as Schneeppert describes it, is like a loop. You have a classical CPU handling the main logic, maybe data pre-processing, post-processing.
The manager, sort of.
Kind of, yeah. And it offloads specific, really computationally tough tasks to the QPU, the quantum processing unit. The QPU does its quantum magic, performs that calculation, maybe gets a speed up or finds a better solution because of quantum effects. Then it sends the result back to the classical CPU.
And the CPU uses that result.
Yeah, it uses that result to continue its process, maybe updating parameters in an optimization, making a decision, and potentially sending another task back to the QPU. It's a continuous feedback loop.
And why is this hybrid approach the main game right now? Why not just focus on pure quantum ML?
Because we're stuck in the NISQ era for now.
Noisy intermediate scale quantum.
Right. Our current quantum computers have, relatively speaking, few qubits, and they're noisy, they make errors. Trying to run a massive, complex ML algorithm purely on one of these NISQ devices, it's just not practical or reliable yet. So the hybrid approach is crucial today because it works within these limitations.
It's pragmatic.
Exactly. It gives us a path to potentially get efficiency gains, maybe scale beyond classical limits for certain problems now. And it also acts as a bridge, a transition towards maybe bigger, fault-tolerant quantum computers down the road.
Makes sense. It's about using what we actually have. So how do you actually build these hybrid systems? What are the main sort of architectural blueprints?
The essay highlights two main strategies. The first one, and it's really prominent, revolves around variational quantum algorithms, or VQAs.
Okay, VQAs.
So in a VQA, the quantum computer prepares a quantum state, let's call it tens theta, a theta wrangle. It does this using a quantum circuit that has adjustable knobs, parameters, theta.
Right, like dials you can turn, and the classical computer's job.
That's the variational bit. The classical computer takes the result from the quantum computer, usually some measurement that represents a cost function, like C theta het angle.
Okay, measuring how good the quantum state is for the problem.
Precisely. And then the classical computer uses standard optimization algorithms, think gradient descent or similar, to figure out how to tweak those parameters, theta, to make the cost function smaller, minimize the cost.
So it's this loop. QPU calculates, CPU optimizes, tells the QPU new parameters, QPU calculates again.
Exactly. An iterative feedback loop. And well-known examples that use this structure are VQE, the variational quantum eigensolver.
Used for chemistry, right?
Often, yes. And QAOA, the quantum approximate optimization algorithm, they both fit this VQA model.
So just to clarify, the quantum computer is doing the tricky quantum state preparation and measurement part.
Yeah, the bit that might be hard classically.
But the classical computer is still doing the heavy lifting on the actual optimization, finding the best settings.
That's the division of labor. That's key to the hybrid approach right now. The classical part guides the search using the results from the quantum calculation.
Got it. And what was the second main architecture you mentioned?
That's often called data splitting, or maybe task partitioning.
Okay.
Here, the idea is the classical computer handles most of the work, the bulk data processing, feature engineering, maybe the overall structure of the model, but for one specific, really tough subproblem.
Like a calculation bottleneck.
Exactly. Like maybe inverting a really large complex matrix, say CO, it hands just that specific task off to the QPU.
Like the SVM example you mentioned earlier.
Precisely that. In a hybrid SVM, the classical part might calculate the kernel function, which defines the relationship between data points. That creates a matrix. Then it sends that kernel matrix to the QPU, which does the inversion, CAP, potentially much faster than classically possible for huge matrices. The result, CAT, goes back to the classical CPU to finish training the SVM.
Interesting. So it's like outsourcing the hardest math problem.
That's a good way to put it.
The essay also mentioned network-based architectures. Is that different again?
Yeah, that's a bit more forward-looking, maybe. The idea there could involve multiple QPUs working in parallel or sequence, maybe orchestrated by a classical control system. Think distributed computing, but with quantum processors involved. Still emerging.
This all sounds incredibly powerful, but also complex. Where is this hybrid stuff actually being used or seriously looked at? Which industries care?
Right. This is where we see the real potential impact. Schniphat's essay highlights applications across science, tech, and industry. Maybe we can dig into a couple.
Yeah, let's do that.
One really compelling area is chemistry and material science.
Which makes sense, right? Quantum mechanics underlies all of chemistry.
Exactly. Simulating molecules accurately is notoriously hard for classical computers because the complexity just explodes as the molecule gets bigger.
Exponential scaling.
Right. HQML, especially using things like VQE, is being actively explored to calculate molecular energies more accurately or simulate chemical reactions. The essay mentions the hydrogen molecule, 8 euros, as a kind of hello world example.
A standard benchmark.
Yeah, showing it works even on current hardware. If we could reliably simulate complex molecules efficiently, I mean, think about drug discovery, designing new catalysts, better batteries, new materials with specific properties. It could be revolutionary.
It's tackling a fundamentally quantum problem with quantum tools, guided classically.
Precisely. Another big area is finance.
Okay, how does quantum apply to money?
Well, finance is full of really complex optimization and simulation problems. Take portfolio management.
Balancing risk and return.
Exactly. You want to build a portfolio that minimizes risk, often represented by something like math BFDT sigma math BFU, while maximizing expected returns, maybe math BFE math BF mu, subject to constraints. That's a quadratic optimization problem.
It gets hard fast with lots of assets.
Very hard. Hybrid algorithms, maybe like QAOA, could potentially tackle these large-scale portfolio optimizations more effectively. And also risk analysis.
How so?
Risk analysis often uses Monte Carlo simulations, running tons of random scenarios to see what might happen. Quantum parallelism, this ability to explore many states at once, could potentially speed up those simulations significantly.
So faster, maybe more sophisticated financial models, better risk assessment.
That's the potential, yes. The essay also mentions quantum-assisted image processing and pattern recognition.
For things like medical scans.
Could be. The idea is encoding image data into quantum states might allow faster analysis of huge datasets relevant for tumor detection, maybe, or even handwriting recognition using things called variational quantum classifiers. And it briefly touches on medical tech and genomics too, where analyzing massive biological datasets is key for diagnostics or sequencing.
These examples really drive home that HQML isn't just theory. People are actively trying to apply it to really concrete, high-value problems across many different fields.
Definitely. But, and it's a big but, it's not easy going. There are some major hurdles.
Right. What are the biggest roadblocks preventing HQML from being, everywhere?
Schniphat lays out several big categories of challenges. First, the technology itself. We're still dealing with uneasy hardware.
Noisy qubits.
Exactly. Scaling up to many more qubits is tough. They have high error rates, they're sensitive to noise from the environment, which messes up calculations.
Uh-huh.
And often, the qubits on a chip don't all talk to each other directly, limited connectivity, which restricts the kinds of quantum circuits you can even run.
So the hardware itself is a limitation.
A major one. People are working on quantum error correction, like surface codes, to try and mitigate noise, but that requires even more physical qubits and is still very much under development.
Okay, so hardware barriers. What else?
Then there are algorithmic challenges, specifically with the hybrid approach. The optimization part, the classical part.
Yeah.
The problems it's trying to solve can be really nasty, high-dimensional, non-convex landscapes with lots of bumps and valleys. It's easy for the classical optimizer to get stuck in a bad local minimum, not the true best solution.
Oh, okay.
And calculating the gradients, the directions to steer the optimization can be tricky and unstable because you're relying on measurements from noisy quantum hardware. Plus, just figuring out the best way to encode complex classical data onto qubits efficiently, that's still a big research question.
So the algorithms themselves and how they interact are challenging.
Right. And then beyond the tech, there are really important societal and ethical questions.
Like what?
Well, transparency. If these hybrid models become super complex, how do we understand why they make a particular decision? Especially it's in healthcare or finance or the legal system.
It's a black box problem again, but maybe even worse.
Could be. Then there's access inequality. Developing and running this stuff takes serious resources, serious investment. Could it create a bigger gap between those who have access and those who don't?
The quantum divide.
Potentially, and just broader questions of responsibility. How do we ensure these powerful tools are used ethically, especially in sensitive areas, when we might not fully grasp all their implications?
Wow. Okay, so it sounds like a lot of fundamental, practical, and even ethical hurdles still need to be cleared. Given all that, what's the vision for the future? Where is HQML heading?
Well, the current hybrid models, the VQAs and task splitting we talked about, are often seen as a stepping stone.
Towards what?
Towards what the essay calls fully integrated quantum classical models. The idea is a future where quantum and classical hardware work together much more seamlessly. Maybe QPUs act more like specialized coprocessors, tightly integrated with classical CPUs and GPUs.
Like a graphics card, but for quantum tasks.
Sort of, yeah. A much tighter integration than the current looping back and forth.
What needs to happen to make that reality?
A few key things. Obviously, much better quantum hardware, more qubits, much lower error rates, better connectivity that's fundamental. We'll need more unified system architectures that allow that closer, faster interaction between classical and quantum. And the software side is huge, two robust software ecosystems. The frameworks like Qiskit, Cirq, Pennylane need to keep evolving to make building and running these integrated applications easier for more people.
So better hardware, better integration, better tools.
Pretty much. And the essay mentions some potential breakthroughs that could really accelerate things. Continued progress on quantum error correction is absolutely vital.
Makes sense.
Maybe the development of new algorithms, super quantum algorithms, designed specifically for these tightly integrated hybrid systems. Progress in quantum-assisted deep learning, maybe new kinds of neural nets we haven't thought of yet.
Okay.
Advances in different hardware types like photonic quantum computers using light, and even stranger ideas like quantum biosystems, applying quantum directly to biological processes. It's a really active research space.
It definitely paints a picture of very rapid development, but also something that needs careful steering.
Absolutely. The potential upsides are enormous, accelerating science, driving new tech, benefiting society. But as we discussed, those are balanced by real risks. Increasing inequality, potential misuse, maybe unforeseen consequences as these things get woven into our world.
It's a future with huge promise, but one we need to approach thoughtfully.
Couldn't agree more.
Okay, so to kind of wrap up this deep dive, we've explored hybrid quantum classical machine learning, HQML. We've seen how it's trying to cleverly combine classical ML strengths with quantum computing's unique principles.
Yeah, using techniques like variational quantum algorithms, VQAs, and task partitioning or data splitting. The goal is to tackle problems that are just too hard for today's classical computers alone.
Right, with potential applications popping up in all sorts of fields: science, industry, finance, medicine.
Exactly. And while there are definitely significant challenges, still technological hurdles with the hardware, algorithmic complexities, and those really important societal questions we touched on.
The potential, according to Yorgos Nepbat's essay, is still seen as truly transformative.
Yeah, it really highlights how crucial these hybrid models are seen, especially in the near term, for both pushing scientific boundaries and driving innovation in industry.
And that essay we've been referencing
Yeah,
by Yorgo Schneepat, it finishes with a pretty strong call to action, doesn't it?
it does. It really emphasizes the need for collaboration between researchers, industry, policymakers.
What kind of actions?
Things like sustained investment in the fundamental research, building teams that have expertise across quantum, classical computing, and the application domains, focusing on actually testing these ideas with practical pilot projects,
Makes sense.
developing education programs to train the people needed, working towards making access to this technology more democratic, not just for a select few, and critically, establishing clear ethical guidelines right from the start, not as an afterthought.
So a lot of work to do on multiple fronts.
Definitely. Maybe we can leave you, the listener, with this thought, kind of pulling together the huge potential and the significant risks we've talked about today. As we develop these incredibly powerful hybrid systems, this capability to unlock immense computational power, how do we collectively make sure we harness that power responsibly? And ensure it actually benefits everyone? It's a huge question. What role might you play in understanding and helping shape that future?
That's definitely something to think about. Thank you for joining us for this deep dive into HQML.
Thanks for listening. Goodbye.